section of the semester, our last set of notes for the fall. We're looking in 6.5. We're going to be looking at reflectional and rotational symmetry. We did our little fun activity yesterday looking at rotation. This is more two-dimensional rotation, but it just was like a fun little break in note-taking, I thought. So when we talk about reflectional symmetry, we've talked about on the coordinate plane reflecting across the X or Y axis, or the line Y equals X. But when we have shapes and we want to know if they have reflectional symmetry, okay, we're checking for a line of symmetry. Okay, so the line of symmetry, remember, serves as a line that you could fold the image over and everything would match up on both sides, right? Does everybody understand what a line of symmetry is? It acts like a mirror dividing the sides of the figure. Okay, so we're going to look at how many lines of symmetry these different shapes here have. Okay, so let me get my line tool here. All right, so this is a square. A square, for instance, is going to have multiple lines of symmetry. What is one line of symmetry that I could draw and I could fold along and everything would match up?
Middle.
Go ahead, Rebecca.
Down the middle.
Down the middle, vertically, horizontally, what direction?
Vertically.
Okay, so I could do vertically right down the center. So that would be a line of symmetry. I heard somebody say horizontally. Okay, if I folded it right, I don't know if I drew that right on the center, but if that was the center, because it's a square, I could go both of those directions. Is that it, or are there more? Because it's a square, I could also fold it diagonally. Both directions diagonally. So how many different lines of symmetry does this have? How many lines did I just draw? 4. I just drew 4. Here, I'll color code them. So I did the first, here was the second, the third, and the fourth. Okay, so I drew 4 different lines of symmetry. So this definitely has line symmetry. It's definitely symmetric across a line. Okay, 4 different lines. Okay, so I'll label those. Okay, so there are 4 lines of symmetry. I'm going to abbreviate symmetry, SYM. Okay, what about in B, this triangle? Is there a place where I could draw a line? Okay, so I heard vertically. So a vertical line right down through that vertex. So what type of triangle must that be if that's a line of symmetry? It could be equilateral. It could also be, it could be isosceles. It just has to be isosceles for us to be able to have one line of symmetry. Okay, now, does this one appear to have more than one line of symmetry? Okay, so I could do through another vertex. Go this way. So this one is what y'all said, equilateral. Okay, so this is an equilateral, so it has 3 lines of symmetry. 1, 2, and 3. Okay, what about this next one? What shape is this? Okay, there's 5 sides. That's a pentagon. Does this pentagon have a line of symmetry?
Yeah.
Where could I draw a line of symmetry here? So just like vertically through that top vertex?
Yeah.
Okay. So I could draw that, and that if I folded it over that, I don't think I drew that right in the center. If I move that over a little, it might look better. Get it right in the center, but you get the idea. So yes, this one has a line of symmetry here. Is that the only line of symmetry, or do y'all see another place, another direction we could draw?
You can do it from all of the angles. You can make a line from every single.
So each of the vertices. Okay, so let's draw one from this right vertex. Oh man, I did not draw that very straight. Let me try that again. There we go, that's better. I could do one from this vertex. Can y'all please stop your side conversations? It's quite distracting. Okay, I could draw one through this vertex, and I could draw one through this vertex. So how many different lines of symmetry is that? 5. Now, what are y'all noticing anything?
Yeah, every like the sides, how many sides kind of lines.
Okay, so in these first 3, however many sides or angles that they had, that's how many lines of symmetry we noticed. Okay, the square had 4, the triangle had 3, the pentagon had 5. Hi. Sure.
Well, who's Ava? Oh, okay. How are you? No.
All right, let's see if this holds true with these other shapes. So those first 3 shapes we looked at, what's different about those than these next 3?
Symmetrical.
Okay, so when you say symmetrical, obviously we're talking about symmetry. They have line symmetry. This, I will tell you, these also have some symmetry. These have lines of symmetry as well. But looking at the type of image that they are, these first 3 are all convex, meaning all of the angles like bow out, okay? Nothing is concave. These images, some of these angles cave in, like this star. This is a concave angle because it's coming inside the figure. Do y'all see that? Do y'all understand convex versus concave? So all of these top ones were all convex polygons. These all have some concave angles. These are not what we call regular polygons. When all of your sides are equal in length, those are called regular. And I actually I added that to our notes on, if you'll flip over to, I think I put it on the back. Yeah, I added it to the bottom here because it wasn't on there. So if you'll flip over to the back bottom, since we're talking about regular, we'll go ahead and put that here. Regular means all sides and angles have the same measure within that shape. So not all quadrilaterals are regular. The only regular quadrilateral means 4 sides. I could have a rectangle. A rectangle is not regular because 2 of the sides are longer than the other 2, right? Okay. I could have a parallelogram, and that's not regular because not all 4 angles are equal. Are y'all following? So a square is a regular quadrilateral. An equilateral is a regular, well, equilateral can be anything, but an equilateral triangle is your regular triangle where all 3 sides are the same, all 3 angles are the same. Okay, and this is a regular pentagon. All 5 sides are the same length, and all 5 angles are equal measure. Okay, so this isn't going to work in every triangle and every pentagon. It only happens in these because these all happen to be regular. Does that make sense? So let's look at these that are not regular. Will you close that door on your way out for me, please? Okay, so in this star, where do you think I could draw a line of symmetry?
It's vertically.
Okay, through that top vertex. That should work. So if I draw one here, so if I fold it over that line, does everything match up? Is that a mirror image? Yes. Okay, where else could I draw one? So if I go through all of these vertices, they happen to also go, if I drew them better, they happen to also go through the convex vertex there on the inside opposite it. So all of those are also lines of symmetry. So this star also has 1, 2, 3, 4, 5 lines of symmetry. So this one is also 5. But a star is not a pentagon. It doesn't have 5 sides. It has 10. Right? So if the rule we had looked at up here, 10 sides, if it was regular, it would have 10 lines of symmetry, but it doesn't. It only has 5 because it's not a regular decagon, right? It's irregular. Okay? So you have to be careful. If it's regular, the number of sides will match the number of lines of symmetry. Okay, what about E? Where could I draw a line of symmetry for this one? Where could I cut this in half and everything is like a mirror image on both sides? Okay, so I could go straight vertically through the center. Left and right are the same. What else?
The other way.
Horizontally. Top and bottom would be the same. Is that it? Where else?
Down the line.
Yeah, along those like X legs, whatever you want to call them. So this one has 4 lines of symmetry. And this is, how many sides does this shape have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a dodecagon. This has 12 sides, but only 4 lines of symmetry. All right, last but not least for the reflectional symmetry. All right, so I could do the same thing here. I could go vertically. I could go horizontally. I could go diagonally. And diagonally the other direction. Anywhere else? No. So A, the square, E, the X, and F, this like arrow cross, all of these have the same lines of symmetry. They all have 4 lines of symmetry.
I thought the star had 5.
I said A, E, the square, the X, and the arrow. All right. You feel like you understand reflectional symmetry?
Yeah.
Okay. All right, good. I think reflectional is pretty straightforward. Yeah, those of you who are released to go to Butler, y'all can get your things together and head down there. Yeah. Okay, so rotational symmetry. And those of you leaving this, I'll post this video so you can watch it and get these notes later. Rotational symmetry is a little, I don't know that it's harder, but it takes some more visualization. Not everybody visualizes rotation as well as reflection. So when you have a figure will have rotational symmetry if there's at least one rotation less than or equal to 180, about a point where the pre-image and the image match, where they're exactly the same. You may think of it as the image, the pre-image, or the image fits inside itself, okay, within less than a full rotation, less than 360 degrees, okay? So what we call the order of rotation, and we're going to use n as the variable to represent that. So the order of rotation, I'm going to highlight here, n refers to the number of times that an object maps onto itself during a full 360 degree rotation. So if an object is said to have rotational symmetry, then its order has to have two or more. Because obviously it's going to have one. If you rotate it 360 degrees, it's going to be exactly the same, right? So that everything's going to have one. If you do a full rotation, it gets back to where it started. So it has to have at least an order of two to have rotational symmetry. Okay. Now the angle of rotation is the smallest angle that you can rotate by for that figure to match itself. Okay. And you find that angle of rotation by doing 360 divided by n, your order. Okay, so we're going to look at a few of these. I'm going to try something. I don't know. We'll see if this works. I'm going to try and take a picture of this and put it on top of itself. Well, it would help if it was the same size. Same size yet? Not yet. Let's see. Oh, no, because I can't see behind it. That's, I thought that might work, but here, let me do it side by side. Okay, so just try to watch. You don't need to draw this. I'm just trying to give you a visual to help you see. So if I go to rotate this star, imagine it's on top of the original. Here's the original. It's not going to move. If I go to rotate this, does it ever look exactly the same as the original? Right there it does, doesn't it? Right there it does. Right there it does. And right there it does. And then full 360, that green dot's back at the top, right? So how many different times did it look like it was exactly like the original? Did it fit in itself, or did it match the pre-image? Okay, let's do it again. One. There's 1, 2, 3, 4, 5. So 5 different times at 5 different angles, that figure was exactly the same as the original. Does that help you visualize the rotation? So I'm going to put that the order of rotation, the n, is 5. That's the order of rotation. Okay. If it helps you, you can like put a dot and show I rotated it this much and it was the same. And then that much more. 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 And I rotated it 5 times and it looked identical every time. Now, if I want the angle of rotation, what did it say to do to get the angle of rotation? Yeah, 360 divided by n. So 360 degrees is the full rotation. What's 360 divided by 5? It comes out to 72 degrees. So the angle of rotation is 72 degrees. That's the smallest amount that I could rotate this and it would look the same. So if I rotated this about the center is in the middle of the shape. So every multiple of 72, this is going to look the same. So I could rotate it 72 degrees and it's going to look the same. I could go 144 degrees because that's 72 more and it would look the same. Do you get the idea? Okay. Let's try to visualize this arrow. If I rotate this arrow 360 degrees, will it ever look identical to the original before I make the full circle? No, this will not. I would have to do my rotation before it looks the same, would have to go all the way around before it maps onto itself again. So my order of rotation is just 1. So that means it's not a 2. Remember, it has to have an order of 2 or more to have rotational symmetry. So this does not have rotational symmetry. So I would say no rotational symmetry. Okay. Now, G, the star, had rotational symmetry of order 5. If you want to put that in words, you can. Okay. All right. What about this X shape? Okay. How much? Let's think of this as the top, or you could think of one of the vertices if you don't want to think of the middle. Okay. If I rotated it this much, won't it look the same? And then that much again, and again, and again. So how many is that? So this has rotational symmetry of order 4. So what would my degree or my angle of rotation be? How many degrees? Yeah, it's 360 divided by 4, which is 90 degrees. Is this making sense?
Yeah.
All right, what about J here? What do y'all think? If I rotated it 90 degrees, it's not going to look the same because, but what if I go 180?
There's 2.
Yeah, won't it look the same if I go halfway, half a circle? Okay, and then I could go the other half. So that's a order of 2. So this does have rotational symmetry of order 2. And what would the angle of a rotation be? 180. Yeah, half a circle. I have to turn it at least half a circle to see the symmetry, the rotational symmetry. Okay, what do y'all think of K? It's going to be 4 again.
Isn't it literally just the amount of things?
So this one, no, because like a rectangle has 4 points and it's only got an order of 2 because it's not regular.
Points.
But if it was a rectangle, if they were pointy, it would still be an order of 2. So it's not the number of vertices. And technically a star doesn't have 5 vertices. It's got 10 because it's got the concave and the convex vertices. Okay. Yeah, this arrow has 1, 2, 3, 4, 5, 6, 7 vertices, and it's only it's got no rotational symmetry. So a lot of them, yes, you can kind of, it's easier to visualize, but it's not a hard, fast rule. Okay, so this one was also a 90-degree angle of rotation. Okay, what about this one? So here, this goes to what you just said. This is round. This is circular. So there are no vertices per se. This is more of an image than a polygon. But we can still determine if it has rotational symmetry. Hudson says 2. Do y'all agree? Because of that slash, for that slash to line up, it would have to go a full 180 before it looks the same. So it does have rotational symmetry of order 2, so 180-degree angle of rotation. Do we get the concept of rotational symmetry? Yes, no, maybe so? All right, so this bottom part, I want you to be able to visualize and compare. Sometimes reflectional and rotational are there. Some of these had both. Like this 4 cross arrow thing, it had rotational symmetry and reflectional symmetry. Same thing with the X. It had both. The star had both. Some images, this arrow, for instance, it has no rotational symmetry, but wouldn't it have reflectional if I sliced it vertically? So some images will have both, some will have one or the other, and some will have neither. Okay? So we want to be able to figure out how to map the image onto itself. So we want to describe 2 different transformations that carry the figure below onto itself, meaning what type of transformation, and it can be reflectional or rotational, okay, could make, what type of symmetry does this figure have? Okay, so what's one? And we're just listing 2 possible. Say it again. A line just vertically. Yeah, so it's got reflectional symmetry. Good. Guys, I need those side conversations to stop because I can't distinguish who's actually participating and answering what I'm asking and who's just off topic. Okay, it's distracting. Okay, so somebody just said, I think Hannah just said, You could have a vertical line drawn here, and this would have reflectional symmetry. Okay. Whoops, I did not mean to do that. So I would say in words, I could say this has this could be a reflection over, and I'm just going to say over a line of symmetry, because there is more than one line of symmetry. So yes, one possible transformation is a reflection over a line of symmetry that would carry the figure onto itself. If you reflected this, it would be the exact same image. Okay, what's another option? Does this one have rotational symmetry?
Yeah.
How many degrees would I rotate it for it to be symmetrical? Or for it to map onto itself?
25. 2.
Let's see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decagon, and it appears to be a regular, meaning they're all equal. So I do 360 divided by 10. So I could rotate this any multiple of 36 degrees, and it should be the same image. So we'll say rotation of any multiple of 36 degrees. So I could go 36, I could go 72, I could go 360, I could go 180, lots of possibilities. Yeah.
Can't you do 18?
No, because let's see. If I use one of these points to look at my rotation, I would have to go 1, 2, 3, 4, 5, 6, 7. Oops, that was not supposed to erase. 7, 8, 9, 10. So there's only an order 10, so it's only 36 degrees. If I were to rotate this 18 degrees, it would still be the same shape, but the vertices wouldn't be at the exact same point. Like this point that's on the top left right now would be right here on this black dotted line. So it wouldn't be flat on the top, it would be pointed on the top. Does that make sense? Can you see that? Okay. All right, what about for this pentagon? What are two transformations that would carry it onto itself? Does this one have any reflectional symmetry? Yes. Okay, and there's lots of possibilities. Okay, I'll just draw this. Well, maybe I'll draw a better one. There, that's better. Okay, so same concept. I could have a reflection over a line of symmetry. Or what's the rotate? Does this one have rotational symmetry? 3, 4, 5. So it's rotational symmetry of order 5, which I would do 360 divided by 5. What did we say that was earlier? 72. So I could say you could rotate a rotation of any multiple of 72 degrees. And that would map it onto itself. So both of these images, because they were regular, had both reflectional and rotational symmetry. You feel okay about this so far? All right, this is just matching. Let's make sure we've got the hang of this. We've got these polygons. We want to answer these 4 questions. Which one of these is a pentagon with reflectional symmetry? A pentagon has how many sides? Okay, so which one of these is a 5-sided shape that has a line of symmetry? Good, E. Okay, B is a pentagon, but there's no line of symmetry. Okay, which one's an octagon? How many sides does an octagon have? Okay, so which one has 8 sides and has reflection symmetry, but no rotation symmetry? Hey, good. Looks like number or G is an octagon, but you could rotate that one. Okay, so no rotation would be A. Good. And the line of symmetry would be vertical here. Okay, which one's a hexagon? How many sides does a hexagon have? Okay, a hexagon with rotational, but not reflectional. Yeah, C is an octagon. D, 1, 2, 3, 4. Yep, that's it. D, I could rotate 180 degrees, couldn't I? Like that. Oops. And it would look the same. So it was D. All right, last but not least, an octagon. So that's 8 again. So an octagon with no reflectional, but yes, rotational. C. Good. This is 8-sided. And again, this is another one. I could rotate it 180 and it would look the same, but there's no line of symmetry. I can't reflect it anywhere. Good. Gentlemen, please stop your side conversation. We're almost done. All right, what about these road signs? Which road sign has only one line of symmetry? Which road sign has only one line of symmetry? Does A have any line of symmetry? Those, I think those are supposed to be arrows on the ends of those. I guess the print is kind of hard. See how this side has an arrow and this side's flat on these? That's flat. That's arrow shaped. That's arrow shaped. That's flat. So because of that, this is not doesn't have reflectional symmetry, does it? So which one does have reflectional symmetry, but just one? B. So the only way I could cut this one for a line of symmetry, what else? Is that the only one or is there another?
D.
Yeah, D, because the 3 and the 0 could be cut this way and be symmetrical. So B and D would work. All right, which road signs have no lines of symmetry? I think I already answered that. Yeah, A, because of the arrows inside there, and then C, because those arrows are going opposite directions. Which road sign is the only one with rotational symmetry? If I rotated B, I would have to do a full circle before that arrow matched up. So that's not rotational symmetry. It's got to be less than 360.
C.
It's A. Because C, the arrows are going other directions. The outer triangle could rotate, but the arrows would always look different than the original until you did a full 360. So A is the only one that has rotational symmetry. And then we already answered what regular polygons are. Guys, shh. Last one. So when you have a regular polygon, in this case, we're looking at a hexagon, okay? And you have your center. We want to identify which of these transformations described would map it onto itself. Which of these are symmetry that this regular hexagon has? Okay, so can we reflect over EG? There's EG. Is that a line of symmetry? Yes. Okay, can we reflect over HX? No. Can we reflect over a G? No, that's not a line of symmetry there. Can you rotate 60 degrees? So let's look at the rotation. What's the order of rotational symmetry here? The order is 6, which means our angle of rotation should be what? 60 degrees. So any multiple of 60 will work. So 60, yes. Now, it's about point M. So around the center, 60 degrees will work. Now, this one says 240, but it's around a different point. It says around point O. That is not the center. So that one is not going to work. Minus 20 is a multiple of 60, and it's around the center. So yes, that one would work as well. So it was A, D, and F that worked. All right, let me stop this video.
I wouldn't. Ugly.